So what actually is an electron? How can it be a wave and a particle at the same time? Well, what it actually is a probability wave. The amplitude of the wave tells you something about where it would be located if it were an actual classical particle. And if you were to look at the wave, what it actually looked like, it would look like what's called a wave packet, which this animation is showing here. There's a lot of closely spaced peaks and troughs that are moving together through space. Now, the higher the amplitude is, the more probable it is that the electron would be located there. Now you can see you're not exactly sure where the electron is because the wave packet is spread out a little bit. Now when you've got an object like a baseball, it's got a large mass, and if you were to look at its wave packet, it is pretty much just a single spike. So it'd be a spike moving along, and if you were to look at the wavelength, it's actually a wave packet, but the wavelength would be actually smaller than an atom. So a baseball is a very sharply focused object. You can easily know where it is, its exact location, and you can easily tell from that how fast it's moving. Not so with the electron. You can't tell exactly where it is and how fast it's moving at the same time. We're going to see that that's one way to state the Heisenberg uncertainty principle. Now, we have a relationship between the wavelength of a particle and its particle-like properties like its mass and its velocity, which collectively are known as the momentum. So the central idea in quantum mechanics is that you've got these little particles which act like waves in some circumstances and like particles in another. In the 1920s, Louis de Broglie came along and proposed a connection between wave behavior and particle behavior. It turned out that after people had figured out what was going on in the photoelectric effect, they could relate the wavelength of a light wave with the momentum that the photons had. Now, what's momentum? Momentum is a measure of the influence that something has during a collision. And for a particle with mass, it's the mass of the particle times its speed. I mean, if you think about what influences a collision, if you've got a heavier thing colliding, like a truck colliding instead of a bicycle, the truck is going to have more of an influence on what happens during the collision than the bicycle will. And the faster things are moving, the more influence they're going to have. So if you take the product, the mass times the velocity, that's the momentum. And that turns out to be related in a very simple way to the wavelength. Wavelength is a wave-like property, and momentum is obviously a particle property. So on this side of the equation, you're connecting particle properties with wave properties, and that is the significance, that is the meaning of this relation, and that also is the central idea in quantum mechanics. Now, you can use this equation a couple different ways. If you look in the book, you can use it to grind out a wavelength if you know what the mass and the speed of a particle is. You can use it that way, and it's instructive to do that at least once. The equation is telling you that if you've got a big mass down here, that's going to make the wavelength smaller, because if you make the bottom of a fraction larger, it makes the fraction overall smaller. If you've got a small mass there, it's going to give you a bigger wavelength. Now the same thing's going to apply with the speed, right? If you've got a particle that's moving very fast, how fast can a particle move? No faster than the speed of light. So if you had a very large speed down there, you'd have a small wavelength. If you had a small speed, you'd have a larger wavelength. Now, the wavelength is going to tell you how fuzzed out the object is. That is, how uncertain are you about where it is and how fast it's moving? That uncertainty in location is going to increase when the wavelength increases. Now, Planck's constant appears in this equation, and this is the same Planck's constant that we found experimentally in the photoelectric effect. It is the same Planck's constant that you use to convert a frequency for electromagnetic radiation into a photon energy. So it relates wave and particle properties with photons as well. Anytime you see Planck's constant appearing in an equation, what you have there is a quantum mechanical equation. Planck's constant would be 0 if there was no such thing as quantum mechanics. This relationship would be meaningless without quantum mechanics. There would be no wave-particle duality. You would just basically have particles. Now, who cares what the wavelength of a particle is? Well, it turns out to have important consequences when we're trying to figure out what's going on with electrons when they're trapped inside of atoms and molecules. If the wavelength of something is big compared to the space that it's trapped in, it is going to behave in an entirely wave-like fashion. And in fact, electrons in atoms and molecules behave like standing waves. And we have no hope of understanding what electrons are actually doing in atoms or molecules if we don't understand their wave-like behavior.